So let me introduce our today's eminent speaker, Dr. Ashish Kumar Mishra. Dr. Mishra received his doctoral degree from IIT BHU, Varanasi in year 2014. He is currently serving as an assistant professor of physics at Samrat Ashok Technological Institute, Vidisha. Prior to joining this institute in 2018, he also has served in Central University of Jharkhand, Ranchi, and Institute of Technology, Gopeswar in various capacities. His research interests primarily focus on the unconventional optical fiber structures and plasmonics. He also completed one collaborative research project sponsored by MOE, Government of India. He is also a life fellow of Optical Society of India, Indian Association of Physics Teachers, and Indian Social Science Academy. He has published almost a dozen of research papers in SCI Index journals and have discharged various administrative responsibilities too. With this brief introduction, on behalf of GBPIT fraternity, I welcome you, sir. And now I request to Dr. Ashish Kumar Mishra, sir, please continue your session onwards. Thank you, sir.
Yeah, thank you, sir. Am I audible clearly and slides visible?
Yes, sir.
Yeah.
You are audible as well as your slides are also visible, sir.
Okay, thanks, sir. So, thank you, sir, for inviting me to deliver the talk and perhaps to interact with learned participants. So I thank from my bottom of heart to the organizer of this Atala Online Faculty Development Program, Dr. Sanjeev Nathani, who have given me opportunity to present my research work, what we are doing here. So presently my talk will be divided, you can say, in two parts. The first part will discuss some fundamental aspects of fiber optics communication. And in next part, I will discuss the research work that we are doing at our present institute. So, as we all are aware that today's life is incomplete without the communications. So during the beginning of these communications, there appeared various forms of communications. So I will focus mainly in very brief on the development of fiber optics communications. So that basically started with the lens guiding systems, where researchers have proposed that by placing converging lenses at appropriate places, we are able to bend the ray of light. So in this way, we are able to trap the light inside through the lenses, and you can send that rays up to certain distances. But this mechanism also, it was not very practically useful, but it have provided us a means to think upon that in this way we are able to design a optical fiber or optical waveguide that can transport your information from one place to another place. So later on, several mechanisms have been developed, and our recent optical fibers that is basically based on the phenomena of total internal reflections that now plays a very crucial role in the sense of your communications. So just I will begin with this very introductory for the newcomers who are willing to prepare their careers in the field of this optics communications. So currently you see that there is almost a 10% of annual growth rate in the field of this optics communication, and it is expected to reach around 10 billion USD dollar up to the end of this 2027. So there is a huge opportunity in the field of this optical communications, and in this, there are various parts of the globe, basically how they contribute in this, how the market of this optical fiber communication is growing. So here you can see as North America, Europe, Asia, Pacific, and all those countries. And basically, how in what what kinds of fibers are being employed in our different applications centers. So basically, three kinds of optical fibers that we employ in our practical applications is single mode, multi-mode, and plastic optical fibers. And you can see from this figure that what is the fraction of this single mode, multi-mode, and plastic optical fibers in different segments. Like as it is very evident that in telecom sector, the role of optical fiber is very much impressive, and that's why it shares almost 50% in this market cap. And the rest other areas also, these optical fibers are being used in like oil and gas, military, and aerospace, and this banking, finance, medicals, railways, and etc. So through these two slides, I try to present that there is very ample opportunity in this optical communication research, those who are wishing to build their career. So just we will start with our discussions that why we need a protected transmission channel for transporting information from one place to another place. So if you might recall that there are several other kinds of communication systems also exist in parallel to your optical communication systems, like free space propagation, satellite communications. But in all those schemes, the information carrying capacity is limited due to several conditions, and also there is a very good chance that your information can be trapped by unwanted person. So it means that your information that you wish to convey from one place to another is not perfectly secure in in other kinds of your existing other kinds of your communication systems. So due to that problems, it necessitated that we need a protected transmission channel that can securely transport our information from one place to another place. And in that, there are certain other kinds of problems that also put forward before designers to think on protected transmission channels, which includes problems of bad weather. So if you recall that your microwave communication systems, so you know that your microwave communication systems basically lie on the principle of line of sight communication. So if there happens any problem in your open atmosphere, so it will cause the fluctuations and your ray will basically refract from its original path. So these problems is also a very major source. That's why your optical signals cannot be transported through your open sky. Next is your flying objects. Flying objects may also distort your signals, and this will also not lead to your secure communication. And another is your line of sight communications that I discussed with you, that in case of your with the optical pulses, this line of sight communication is not feasible, since if there happens a temperature gradient of even 1 degree centigrade or less, so light will diffract, light pulse will deflect equal to its diameter by traveling a distance of 1 kilometer. It means that if you launch your light pulse through your open atmosphere, and you know that the temperature varies as you go upwards. So due to that temperature gradients, the line of sight communication is not possible with your light pulses. And also, your light pulses gets randomly aberrated when your laser beams passes through your open atmosphere. And most importantly is that there is also fair chances of having crosstalk problem when you launch your pulse through your open atmosphere. Crosstalk basically represents the coupling of two beams. One is your signal beam and another is your unwanted beam. So it will lead to the loss of information as well as the quality of information. So that's why this crosstalk problem is avoided in our communications. So all these listed problems basically necessitated that we need to have a protected transmission channel which securely transport our information from one place to another place. So as a solution of this, your optical fibers comes into existence. So basically, if you see this in this figure, so optical fiber basically consists of a central guiding region that we call as core, surrounded with another region that we call as the cladding. And these two regions basically play part in transporting the informations, and rest other regions just they provide the mechanical strength to your optical fibers. So why we should not, now the question is, you may ask that why we should not use bare optical fibers. Bare optical fiber means it contains only core region, not a cladding region. So, to understand the purpose of adding cladding to the core region, just you can see that it ensures the total internal reflection phenomena throughout the length of the fiber. If cladding is not there, then the total internal reflection phenomena, which is the building blocks of guidance of your optical pulses through your optical fiber, it cannot be ensured throughout the length of your fiber. So this cladding basically ensures that this total internal reflection phenomena should occur throughout the length of the fiber. Also, it reduces the crosstalk, and this basically protects your unwanted signals to enter into the core. Since the unwanted signals which come from outside, they will be reflected back into the same medium. So that's why that rays cannot penetrate into your core region, and hence the coupling of this your unwanted signal with your light signal becomes insignificant, and hence this cladding also ensures that the crosstalk problems is eliminated. And there are several other issues that have been handled by the cladding, so I will not go in much detail. And if you go into the literature, then you will find that cladding also minimizes the cone angle. So you can recall that when the light pulse basically launched from your laser source, so it enters into the fiber in the form of a cone. So due to the variations in the refractive index of core and cladding, the value of this core angle becomes smaller and smaller by changing the value of refractive index of cladding. So it also basically reduces this core angle. Otherwise, you will have to use your fiber of larger core size, and in this way, if you go for larger core size, then the single mode operation of optical fiber will not be feasible. So that I will discuss in our coming slides. So to this, you should be very clear that why we should need a protecting transmission channel and what is the purpose of using cladding in our optical fiber. So some of the salient features of optical fibers that you should know that basically if you use your optical pulse that that is moving with a signal of 10 gigabit per second, then it will have the ability to transmit any of the following information per second. That is 10,000 of 1,000 of books you can send in a second. 1,030,000 voice channels can be handled with 16 high definition TV channels can be handled with this 10 GB per second signals. So you can see that with this your optical communications, it basically raises a very high information carrying capacity, and you know that information carrying capacity of a communication system is directly proportional to the frequency of the signal or carrier frequency. So in this way, if you go from microwave to optical range, so you know that in microwave range the typical frequency ranges are of the order of 10 power 6 hertz, but in optical range it goes around 10 power 15 hertz. So you may see that around 10 power 9 times the capacity will be enhanced if you move from microwave communication system to optical communication systems. But at the same times, due to with all these features of your optical wires, there is also some limitations that basically limit the information carrying capacity of your optical fiber, and in which you should know that attenuation and dispersion, these are the two major sources which affect the capacity of your optical communication systems. So I will discuss these attenuations and dispersions in our coming slides. So this typically information carrying capacity that typically defined by this formula that you can as C equal to bandwidth times log of 1 plus signal to noise SNR, where SNR, this represents your signal to noise ratio. So from this equation, you see that if the bandwidth will be wider, then information carrying capacity will also be higher, as well as if the signal to noise ratio is higher, so in that case also the information carrying capacity will be high. So through these two principles, it ensures that in your optics domain, the available information carrying capacity is much higher. So theoretically, we predict that the available bandwidth is approximately 10% of your carrier frequency. So if you look at your very high frequency radio systems which operate on 100 megahertz, so the available bandwidth will be only 10 megahertz. And in microwave systems which operate on 10 gigahertz, so available bandwidth will be 1 gigahertz. But in optical systems which operates on thousands terahertz, the available bandwidth will be 100 terahertz. So you may see here that how enormous available bandwidth is available in optical systems. But practically, if you look at the practical situation, so you will see that although there is a very huge available bandwidth in optical communication system, but all these available bandwidths are not fully utilized in today's optical communication system, since still we have not fully migrated from electronic to optical domain. that is, still there are some devices which are employed to convert your optical signal into electrical signal and then back from electrical signal to optical signals for processing purposes. So in this way, the bandwidth limitations come into play, and that's why these, with the application of your electrical devices, it puts your inherent bandwidth limitations. So that's why in today's there is effort from all over the world that we have to fully imply our optical devices, and in these directions research have been going on at different places of the world. So in this, you can see that basically when we talk about the bandwidth, so it doesn't give us any practical sense unless we talk about the bandwidth which is available up to what distance. Since if you look at for very short distance, so you may have a very high bandwidth in your other communication systems also, but that available bandwidth is limited to very narrow short distances. So that's why a product of bandwidth with the distance that we call as the modal bandwidth, this basically tells us the technical capacity of any communication systems. So in fiber optic cable, you see that the available bandwidth is around 4,700 megahertz with the speed of 10,000 megabits per second in case of your multimode fibers, and 1040, 100, 200 gigabits per second with your single mode fibers. And that available bandwidth is almost around up to 80 kilometers. And the price which costs for the manufacturing of this fiber optic cable, this comes around $7 to $8. And in case of your twisted pair cable, so that its speed is around 10 gigabit per second, and available bandwidth is also 4,700 megahertz, but this available bandwidth is limited only up to 100 meter. So here you can see that the available bandwidth in your twisted pair cable is same as in case of your fiber optic cable, but that available bandwidth is limited only for 100 meter, while in case of your fiber optic cable, it is available around up to 80 kilometer. And also the manufacturing cost, it comes around $8 to $9. So although it is also a cost effective, it is not much expensive compared to your fiber optic cable, but in terms of the modal bandwidth, so there is no comparison with fiber optic cable and twisted pair cables. Next is your coaxial cable transmission systems. So there is no specific speed in this coaxial cable systems, and the available bandwidth is 750 megahertz. And this available bandwidth is only limited up to 500 meter, but its manufacturing cost is very much high. That is around 10 to 13 US$. So it is also not an economic. So with all this peculiarity of your optical fiber communication systems, we must also have to know that there are some disadvantages of your optical communication systems, and primarily it tells us that the installation cost of this fiber optic cable is very high. Next is the interconnects, that is the part which connect your fiber to other processing systems, that also are very costly. Although with respect to your fiber optic cable, its cost is very much low, but with these optical interconnects, its cost becomes much higher. So, but researchers are trying to develop your cost-effective optical devices, which basically reduces the price of these interconnects. And also, the repairing and maintenance process is in your optical fiber communication system must be done by a sophisticated tools and very trained person. It is not just to your electrical wire that you connect with them. You need to have a splicing and with connectors. So these are some of the disadvantages of the optical communication systems, but these disadvantages are very much insignificant compared to the advantages of your optical communication systems. So now I just outline to what are the challenges, and we know that challenges always brings the opportunity. So I will just outline here that what are the challenges and opportunities in optical communication systems. So first one challenge is that all optical communication network. As I already mentioned that in processing of the signal, we require our all optical processing systems. But still today we employ certain electrical processing systems since we don't have so much reliable as well as effective our optical processing systems, and that's why our optical communication network is not fully optical. It's basically a hybrid network which implies both your optical as well as electrical processing systems. So if you recall that you again know that laser is the source which produces your light pulses, and that light pulses are basically passed through your optical fibers, and then that pulses are received at the receiver end, where these optical pulses are now converted into electrical pulses for the driving of your next associated circuitry. So, so this basically puts an opportunity before your researchers and those who wish to build their careers in this optical communications domain, that still today worldwide researchers are trying to fully employ this all optical communication network. Next is your multi-terabit optical networks. So we know that with the evolution of different multiplexing techniques, the information carrying capacity of the networks have been improved. But with the evolution of dense wavelet division multiplexing technique, now 4 terabit networks using 40 gigabits per second data rate presently exists. And but the target is to achieve even more higher bandwidth with 100 GB per second data rate economically. Okay, so this again opens the opportunity for the persons who are seeking careers in this optical communications. And still, if you compare with your existing networks communication systems, so they are basically intelligent in the sense that they allocate the bandwidth depending upon the demands. So you know that at certain networks there may be, at a certain time there may be less traffic of the signal, but at certain networks there may be a high traffic of networks. So that allocation of bandwidth is implied very intelligently by in the existing network systems, but that have to be implemented in case of your optical networks. And further, the improvement in laser technology, and as we know that single mode tunable lasers are of great importance for future coherent optical systems. and these tunable lasers lays in a single longitudinal mode that can be tuned to a range of different frequencies. So basically, we know that still, although the laser lights are highly coherent, but still we can say that they are not perfectly coherent. Okay, but we need a laser source that whose wavelength can be tuned externally in order to achieve a certain goals. Okay, so in that case, it requires a tunable lasers that we can do it either electrically or manually instead of placing a new laser source in place. So these are the some our areas where research are going on, and you need to put your sincere efforts in these directions also to build your careers. So with all these fundamentals about this optical fiber communication systems, now we will discuss in some more detail about the constraints that basically limits the information carrying capacity of your optical fiber. So in this, first we discuss the different kinds of losses that your light pulse encounters while propagating through your optical fibers. So broadly, that losses can be classified typically in two categories. One is your intrinsic losses and another is your extrinsic losses. So in intrinsic losses that incorporates the absorption losses that appears due to the UV absorptions or infrared absorptions. And it is directly connected with the material components of the glass. Means with what kinds of materials your glass have been manufactured. So accordingly, the UV absorption and infrared absorptions will give you the magnitude of your absorption loss. And in case of extrinsic losses, so this basically appears due to the presence, primarily due to the presence of your hydroxyl ions that remain in during the fiber drying. So this, due to the presence of this hydroxyl ions in the glass fibers, it basically leads to the very high amount of losses. So so this presence of hydroxyl ions that should be avoided during the fiber pooling, and this can be done by this vacuum deposition techniques. So you now with the nowadays the fibers, glass fibers which are available, I think they have a very small fraction of this presence of this hydroxyl ions, and around 1 part per billion. So nowadays this presence of this the loss due to the presence of this hydroxyl ions is not a major issue with our improved fiber drying techniques. Another kind of loss that results that we call as the Rayleigh scattering, and you know that Rayleigh scattering is inversely proportional to the fourth power of the wavelength, and it basically appears due to the local inhomogeneities present in the fiber. So local inhomogeneity that leads to the refractive index fluctuations, and due to the fluctuations of these refractive index, the condition of uh, total internal reflection is not met always. And you know that if the condition of total internal reflection is not met always, so in that case, it will lead to the possibility of leaking out of the signal from the core of the fiber. So here you see that light has been passed, launched into your core of the fiber, and due to the presence of this local homogeneity, it leads to the refractive index fluctuations, and your light gets bent, and it meets to this core cladding interface at an angle that is smaller than the critical angle. So if the light meets this core colliding interface at an angle less than critical angle, then part of the light will get reflected, and this reflected light will amount to the loss of the signal. So that should also be avoided. And next, another kind of that appears due to the scattering of light pulse that we call as the Mie scattering, and this basically results due to the core colliding refractive index variations over the length of the fiber. If throughout the length of the fiber, if there is any variation between the refractive index of core colliding at this interface, so it will lead to the a new kind of scattering that we call as a Mie scattering. Although it is not a significant source of loss of your optical pulses, but still it should be remembered that this also leads to the loss of the signal. So with these sources, you know that if the losses appears with your pulses, so you frequently need to repeaters or amplifiers in order to increase the strength of the signal. And with the introduction of this frequent amplifiers or repeaters in your optical networks, so it basically increases the cost of your optical networks. So that's why it is avoided to use repeaters or amplifiers frequently, and hence our effort is to minimize these sources of losses. So I have briefly introduced you that what are the sources of losses, and next is your different kinds of dispersions in optical fibers. So as you know that attenuations leads to the frequent use of your repeaters or amplifiers, but dispersions limit the information carrying capacity of your optical fiber, or in a more another way you can say that it limits the speed of your network. So dispersion basically refers the temporal broadening of light pulse as it propagates down the fiber. So here in this figure you can see that the light has with different components. This is the center light with its center component as lambda naught. This component has somewhat higher value of wavelength as lambda naught plus delta lambda upon 2. And in this third case, it has the smaller wavelength, that is lambda naught minus delta lambda upon 2. So if your light pulse have this spectral component of these wavelengths and they have been launched into your fiber, so you know that your refractive index also varies with this wavelength. Okay? So although your light pulses have been launched into the fiber, but they will reach to your receiver end at different intervals of time. And due to that different interval of time, they lead to the broadening of the pulses. So that you can see here that your input pulse is like this one, and after traveling a certain distance through your optical fiber, it now have broadened here. So once the signal becomes broadened, so in that case, the amount of signal that you can transport per second that you have to come up with, means you have to ensure that light pulses should not overlap with each other, and hence you are constrained to send less number of pulses per second. So in this way, your dispersions limits the information carrying capacity of optical fiber. So there are different kinds of dispersions. So you know that the different spectral components of a pulse travel at different group velocity, and that we call as the chromatic or material dispersions. And as we know that our modal power distribution between this core and cladding depends upon the wavelength. And if there is any variation in the wavelength of your input power, so there will be a corresponding variation in the modal power distribution between the core and cladding. Okay, and due to that variation in core and cladding, the effective index will fluctuate between the refractive index of core and cladding. It means the value of effective index will not be a constant one. Instead, it will be fluctuating between the values of core and cladding. That is the actual refractive index that your light pulse will see when it will pass through your optical fiber. So this due to variation of this effective index, it will lead to the delay distortions, and that we call as the waveguide dispersion. And from here you also see that if the power content is higher in the core region, so it means the value of effective index will be near to the value of refractive index of core. So from here you can also see by the plot of this effective index curve that what amount of power is contained in the core of the fiber and what amount of the power is contained in the cladding of the fiber. And another kind of dispersion that we call as modal dispersions, and that basically you can say this is a multi-path dispersion. And you know that if there appears a refractive index variations in core and cladding, so it will lead to a different path, means the angle of striking at the core cladding interface will go on changing, and due to that change in striking angle at the core cladding interface, sorry, just a moment. So due to that change in the stacking angle at the core cladding interface, the path length traveled by different rays becomes larger and larger, and hence this will lead to the broadening of pulse that we call as the modal dispersion. So although the problem of modal dispersion is not associated with your single mode fiber, since your single mode fiber supports only one mode, but it is also a crucial factor in case of your multi-mode fibers, since you know that multi-mode fibers are very frequently employed in your local area networks, and single mode optical fibers, they are employed to transport your information over a long distances. So this modal dispersions is play a very crucial role in determining the ability of your local area networks. So just I will briefly discuss about the proto-internal reflections. So as we all know that when the light meets the interface of two media, so part of light gets reflected and parts of light gets refracted. So refracted light basically leads to the loss of the signal. So that's why this part should be avoided in case of your optical fiber communications. So here the light is launched at this interface at an angle of incidence of phi 1, and it gets reflected at an angle of phi 2, and this is your reflected part. Now if you increase the angle of incidence, that is phi 1, if you increase its value of angle of incidence, so there appears an angle of incidence at which your no part of light appear in your second media, means your part of your almost maximum parts gets reflected and very small reflected parts travel along the interface. So the angle of incidence corresponding to which the refracted part sees, that we call as critical angle. So in case of your optical communications, it is ensured that the light should be launched at the co-colliding interface at an angle greater than this critical angle, so that your all light will get reflected into the core region and no part will come out from this core region. Okay. So this is the basic principles that underlies basically the operation of your optical fiber communication. And if you go for this analytical treatment of this optical fiber communications, so you need to solve your Maxwell equations. So basically, I have not covered here the mathematical part of this. So the interested one can look into the literature. So, but just I am trying here to present you that if you go for the analytical treatment for the evaluation of performance of your this optical fibers, so you need to have solved Maxwell equations by applying appropriate boundary conditions. So in the core region, as it is required that your wave should be oscillating and propagating, so the appropriate field representative will be Maxwell Bessel functions. If you use your cylindrical geometry. And in the colliding region, you expect that no wave should appear, so the appropriate Bessel function will be modified Bessel function of second kind, and their plots have been shown here for different indices. And with writing these field components in the core and colliding regions of your fiber separately, and by implying these boundary conditions that your light rays meet at the core interface, you will reach to a characteristic dispersion equations that I have written here. So here you see that the all these parameters are known, only we have to find out the value of this beta. So this beta that basically represents the longitudinal component of your wave vector that that you can solve, or its value you can obtain by using your appropriate numerical techniques. So I am not going to discuss in much more detail about the mathematics. So the interested one can look into the literature. So the solution of that characteristic equations basically determines that determines the performance of your optical fibers. So in that sense, I will discuss briefly about the modes and their designations. So now, there are two approaches to classify the designate the modes. One is our ray optics approach, and another is our wave optics approach. So in ray optics approach, what we see that the resultant wave that you get, or that your fiber propagate fiber comes in the form of two different categories. One is your meridional rays, another is your skew rays. So meridional rays that basically travels along the fiber axis. So the rays which travels along the fiber axis that we call as the meridional rays, and the rays which travels in skew fashion, that is, it successively gets bent, so that we call as skew rays. So meridional range, that is basically equivalent to the lowest order mode in terms of your wave optics representation, and skew range that represents your higher order modes. So if you imply the wave optics approach, so here you can classify the modes in three categories. One is your transverse symmetric modes that contains your transverse electric and transverse magnetic modes. And another is your hybrid modes, which contains your hybrid electric and hybrid magnetic modes. And third one is your linearly polarized modes. So this linearly polarized mode basically comes from the special consideration of the solution of this characteristic dispersion equations, and in the condition that if the refractive index between core and cladding, that is N1 and N2, is very much small, so in that case we can approximate them to be equal, and under that condition the solution obtained of these characteristic equations appears in the form of linearized polarized modes. And hybrid modes basically this represents HE and EH modes. So if the component of magnetic field dominates over the electric field, so that kind of mode we call as HE modes. And if the component of electric field dominates over magnetic mode, so that mode you call as EH modes. So modes are nothing but you can define them as interference patterns which appears in the form of your propagating and forward propagating and backward propagating waves. And mathematically, you can define the modes as these are the solution of Maxwell equations satisfying the given boundary conditions. Okay, so the solutions that you get of these characteristic equations that you call as a mode. So the fundamental modes that in case of our fiber optics we call as HE mode, and it is the fundamental mode in the sense that you can excite this mode at any frequency. But all other modes, they have a very specified cutoff value of cutoff frequency. Means below that frequency, that modes cannot exist in that particular fiber. So I hope that I have discussed the fundamental aspects of our this fiber optical communication systems, and I have presented you or I have sensitized you somewhat in the fundamental aspects of this fiber optics. So in second part now I will discuss the work that I am taking here at my place, so that we will discuss with you some of the results that we have produced. So this is our plasma cladded optical fiber. So as we all aware that day by day the requirement or the informations that we are seeking from our source, that is increasing enormously. So you know that before you use your mobile phones only for your voice communications. Now you use your mobile phones for this video communications, use of internets and all those things. So it means that day by day the requirement of higher bandwidth is increasing. And we know that in our optical communication systems, there is enormous available bandwidth, but that available bands are not fully utilized. So our effort through these works is to enhance the capacity of our existing communication systems by managing the disperser effects as well as loss effects. So typically we have proposed here, this is the central guiding region of the fiber that we call as the core of the fiber, and it is made of your glass. It is surrounded with your dielectric cladding region, and in this dielectric cladding region we have provided certain range of gaseous plasma region. Means in this part your glass have been removed and your gaseous plasma region has been created, and this gaseous plasma region is connected with your external DC control voltage so that we can control the properties of plasma. So plasma, I think you all are aware that it is nothing but the fourth state of matter, and it shows the quasi-neutrality property. It means that throughout the plasma, the charge neutrality condition is not fully satisfied, but in certain regions this is fully satisfied. So I will briefly present to you some properties of this plasma, that how this works basically. So if you write the refractive index, that which is very much important to explore the optical properties of any media, so that you can write as square root of 1 minus omega p square upon omega times omega minus I gamma, where this omega p represents plasma frequency, omega represents this your signal frequency, and this gamma represents your loss coefficients. And this loss coefficients basically appears due to the collisions between electrons and ions in the plasma region. So if you take your plasma at low pressure, so in that case the collision between electrons and ions becomes insignificant, and hence in that condition you may ignore this loss coefficient. So in that approximation of low pressure, you can approximate this equation as square root of 1 minus omega p square upon omega square. So under this condition, this will be the governing equation for the variation of refractive index with respect to your plasma frequency and signal frequency. And your this plasma frequency is typically defined in terms of square root of E square n upon me epsilon naught, where E is the electronic charge, n represents your electron density, me this represents mass of the electrons, and epsilon naught is the permittivity of free space. So with these equations you see that your these three quantities, that is E, me and epsilon naught, these are constant. Only what we can do with is to vary this electron density, that is n. So by implying this DC control voltage, we basically effectively we are tuning the value of this electron density, and with the tuning of this electron density, we are able to tune the refractive index of this plasma frequency. So this is the entire our thought behind the consideration of this plasma cladded optical fiber. So I will just present here the results that we have deduced up to now, and we will discuss here. So first is the mode field diameter. So typically mode field diameter, if you take a Gaussian pulse, so this is your Gaussian pulse. So if its power reduces to 1 upon E square of its peak value, so the spread in that Gaussian pulse corresponds to the mode field diameter. So this is the typical definition of a Gaussian pulse, and an empirical formula to calculate this mode field diameter is given by Peterman, that is equal to twice a 0.65 plus this term plus this term, where V is the dimensionless parameter that we call as V number. And this V number is very important fiber parameter, which directly tells us that whether your fiber is single-moded or multi-moded. So if the value of this V number is less than 2.405, so your fiber is single-moded, and if its value is equal to or greater than 2.405, so in that case your fiber will be multi-moded. It means in single mode fiber, your fiber will support only one mode, but in case of multi-mode fiber, it will support more number of modes. So, but the definition of this mode field diameter with this Gaussian pulse is limited only when the size of your pulse is exactly Gaussian. As we know that the laser pulses which generate your optical pulses that are not perfectly Gaussian in its shape. And if you go for your higher pulses, so they much deviates from this Gaussian shape. So in that cases, it is very difficult to deduce the mode field diameter in terms of this definition. So under that conditions, this formula is very much useful to calculate this mode field diameter. So in case of our this plasma cladded optical fiber, we have plotted a graph between this modal field diameter and delta. This delta parameter represents the ratio of plasma frequency to your signal frequency. That is the ratio of omega p to omega. So here you can see that by adding this ratio of plasma frequency to this signal frequency, we are able to tune this mode field diameter. So this is very interesting result that we have deduced with this plasma cladded optical fiber, and that also have been published in Optic in this 2021. Since you know that mode field diameter plays a very crucial role when you couple two fibers or when you couple other associated circuitry with the fiber. Since a mismatch in mode field diameter amounts a huge loss, and that's why this the matching of mode field diameter is very much required. Suppose if you are joining two fibers, so the light which is coming from the one fiber is fully coupled into, will be fully coupled into the second fiber only when the mode field diameter matches from this first fiber to second fiber. If there is any mismatch in the value of this mode field diameter, so it will lead to huge amount of loss. So that's why here you can see that with our considered signal frequency and with this variation in plasma frequency, we are able to tune here the value of this mode field diameter from 0.85 to around 1.15 micrometer. So means if you imply your plasma cladded optical fiber at the place of joints of two optical fibers, so in that case you are able to minimize the value of these coupling losses. And the most important thing that we get here, that we are doing this in online condition, means we are not we are just riding this DC control voltage. We are able to manipulate the value of this mode field diameter. So this is very important, very interesting results. Next is we have in this plot we have presented here the effect of variation of this plasma frequency on this beta. So here we have plotted these two curves for omega p equal to 10 power 15 Hz and omega p equal to 10 power 10 Hz. So here you can see that when the value of omega p and omega are comparable, so in that cases the tuning of plasma frequency give us the significant result. And when this ratio becomes much nearer to 1. So in that case, the effect of this plasma frequency becomes insignificant. So what it tells us that uh, here you see that when this value of plasma frequency is comparable to omega, so here you see that the two curves are quite dissimilar with each other. But when this approaches to the value of your signal frequency, they now becomes almost similar and traces the same path. So this with these we deduce the result that if you keep the plasma frequency that should be equal to the nearly equal to the not equal to the nearly equal to the signal frequency. So in this way that you may use for your tuning. And in the inset of this figure, we have plotted these two curves in the C band of our communication spectrum. Since you know that whatever the peculiar properties shown by your proposed fibers, if they do not lie in the C band of communication spectrum, so that are basically meaningless in application point of view. Since your whole optical communication systems lies in the C band. C band means its wavelength ranges from 1530 nanometer to 1570 nanometer. So whatever the tuning that you are getting here, if it is beyond the C band, so that is basically meaningless with respect to our existing optical communication systems. So here you see that in this C band also these two plots are quite dissimilar, okay, in respect of their magnitude, okay, for plasma frequency 10 power 15 Hz and 10 power 10 Hz. So once if you are able to tune this beta, then you are able to tune other fiber parameters like your group velocity, your group velocity dispersions, and all those things. So it means that this is a very interesting results, and that also have been proved by plotting this beta in terms of omega p, that is your plasma frequency. So here you see that when omega p reaches to the signal frequency, so in that cases you see that the value of this beta decreases drastically. So in this region, if you keep your plasma frequency above 10 power 13 Hz, so that plasma may be utilized in tuning the guiding properties. So in this figure, we have plotted the usual modal dispersion curve, that is the curve between your normalized propagation constant B and normalized frequency V for plasma frequencies 10 power 15 Hz and 10 power 10 Hz. And the part of this dispersion curve within these two vertical lines represents the part of your C band of your communication spectrum. So again here you see that the flattening of these modal dispersion curves are more prominent in C band. For this 10 power 15 Hz, it starts from here and goes like this one. And for this 10 power 10 Hz, this part lies in this way. So this basically this flattening you can manipulate by manipulating the value of plasma frequency, and this convincing property may be utilized in your dispersion management. So this is again a very interesting results, and all these results have been published in our this update in 2021. So now we have further extended our studies with respect in context of our this plasma cladded optical fiber. So here we have plotted a curve of group index, and you know that the value of this group index determines that whether your proposed fiber is showing slowing property or not. You know that the slowing property of optical pulses are very much useful in your optical memory devices. Since you cannot do with your usual light pulses, since their speeds are very high, and you cannot do any manipulations with such a high speed light pulses. So, in order to manipulate, our sense of manipulation is to modulate our other processing. So, you need to have a slow pulses. So this value of this group index, basically this determines whether your light pulses are getting slower down, and what is the value of your group velocity dispersions. So again, this group index is typically defined as n minus lambda times dn upon d lambda, and this have been plotted for different values of plasma frequencies and different values of co-refractive index. So again, here you see that we have a family of curves for different values of plasma frequency and different co-refractive index. So you see that the flattening and the magnitude of this group index is quite dissimilar, and you can manipulate this slope of this group index curve as well as the magnitude by manipulating the value of this plasma frequency and the value of this co-refractive index. So we are basically interested only in this part of the curve, since this is the C band of your communication spectrum. So here you see that can be manipulated by appropriate manipulating of plasma frequency as well as core radius. And in next, we have plotted here the effective index, which is typically defined as square root of b square v square upon k square plus n2 square for two different values of plasma frequency as 10 power 15 Hz and 10 power 14 Hz. And as I previously told you that with the plot of this effective index curve, you are able to say that what fraction of energy or power is being carried out through the core of the fiber, and what fraction of the power is being carried through the cladding of the fiber. So here you see that the slope as well as the magnitude are quite dissimilar in cases of plasma frequency 10 power 15 Hz and 10 power 14 Hz. So again you see that this can be manipulated, effective index can be manipulated by manipulating the value of refractive index of plasma media. So, but still we are working on to find out with this effective index curve that what fraction of power is being carried through the core of the fiber and what fraction of the power is being cladding through the fiber. So that is the result that we are still working upon. And this work has been published in our results in optics in 2021. So that I think here it is mentioned. And based on these our reduced results, we have proposed an optical modulator. So you know that an optical modulator is a device which is utilized for intensity modulations, and it is nothing but a Mach gender interferometer. And this is basically a combination of two Y junction waveguides which are connected side by side. So your input light pulse is that is launched through the laser input fiber. Now it splits into two parts. One propagates along this arm and another propagates along this arm. And this arm of your Y junction waveguide is your single mode fiber, and the beam which travels along this single mode fiber basically serves the purpose of your reference beam. And other part that travels along the second arm of your this Y-shape waveguide, basically now its properties are manipulated with this plasma cladded optical fiber, and once and they are again back combined and processed for next. So in this way, you get your intensity modulated pulses at the output of this magenta interferometer. So again, I am pointing here that in your other available your magenta interferometers. So this second arm basically consists of your non-linear materials. Since the non-linearity property of the materials are being implied to utilize for intensity modulation. But in this case, in our this proposed scheme, we are not utilizing here the non-linear property of your guiding media. Instead, we are utilizing the plasma property of this plasma cladded optical fiber to for the intensity modulation. And that you can do in online condition. That is, you can do it dynamically. So this proposal has also been published in our results in optics in 2020. So with all the discussions, I hope that you must have enjoyed our this almost 1.5 hours sessions. So this is all about what I wish to share with you and what I am doing here. So now it's open to you for your any further queries.
Participants are requested to ask their queries. If anybody is having any doubt, he or she can raise their hand or they can unmute themselves and ask the query. The forum is open for discussion. Anybody, if you have any query, you may please ask.
Hello.
Yes, sir. Please.
Hello.
Yes.
Good afternoon, sir. Sir, can I have the 13 number slide again?
13th. Yeah.
Yes, sir.
Yeah. This one?
Yes, sir.
Yeah.
Sir, can we have these higher modes in single mode fibers?
No. Single mode fibers can be launched only through your fundamental modes. Otherwise,
Okay.
if you go for your higher order modes, so it will not be possible to restrict your all other modes. Okay, suppose if you go to excite your HE21 mode, so the cutoff frequency of this ES21 or EH11, it may be lower. So that mode may also be excited. So in this case, your fiber will not be a single mode.
Okay, sir.
Okay. And otherwise, suppose if you wish, suppose through your fiber, if you wish to get only one kind of mode, then you need to imply a mode filter. And that basically complicates the networks.
Any other query by the participants?
Okay, so I think, sir, there is no query. So those who are interested, they may write directly at my mail or through the sir. So I think my mail is shown on the first slide. So you may get my email ID, and if you wish to have any queries, then you may write me, and I will surely try to address them. And one more thing, that in the sense of analytical facilities that is available at my labs, so here I am using RSoft as well as this your console multiphysics So we have both your wave optics and ray optics modules. So with that software, you can simulate your structures. So that is also open to you. If you are interested, then you may also use that facilities that is available at my place. But for that, you need to just write an email to me, and you have to mention the kinds of work that you wish to do. So this is what I wish to share with you.
Sir, I think someone is saying, someone is
Yeah.
having some second
Sir, can
query.
you please say the first slide again? Actually, I missed that slide. That's why.
Yeah, just I am sharing. Now it's visible?
Yes, sir. Yes, sir. Thank you,
Uh,
sir.
uh,
Okay, so participant can note down the email ID of the sir, and in case of any query, they can individually mail him. Okay. So with this, the session is come to an end, and thank you, Dr. Ashish Kumar Mishra, sir, for sparing your valuable time with all of us. It was a great session, and I hope that all the participants are getting benefit from your wisdom. So with this, I think I think we can conclude the session here, sir.
Okay.
Okay.
Thank
So
you very much,
thank you.
Mishra sir.
yeah. Thank you, sir. Thank you.
Thank you, sir. On behalf of GBPIT fraternity, I sincerely thank you for sparing your valuable time with us. Thank you very much, sir.
Yeah, thank you, sir. Thank you, and thank you for giving me
Thank you.
opportunity to share my works.
Thank you very much, Mishra sir. Okay.
Okay, so participant, the next session is from 2:30 p.m. onwards. So please join the session as per the timing. Link will be shared to you via mail as well as WhatsApp. Thank you. Thank you very much.